Hello guys, this is Piyush Raut from Electrical Engineering Department and this is Digital Signal Processing Lab 6th. So in this lab we have to design a filter to remove the baseline having a frequency below 0.4 Hz using the PoleZero placement method, and we have to implement this algorithm on Arduino for the following signals. We have been given the signals which are PPG signal which is sampled at 80 Hz without baseline, with baseline signal, and the PPG signal with baseline and a 30 Hz power line signal. So in what we have studied about the pole zero placement method into the theory course. So here what we are going to do is, what the pole zero placement method says is, whenever we are designing an analog filter, if you want to maximize the gain of a certain frequency, we generally place a pole at that frequency, and if we want to minimize the gain of the following component, we just place a zero on the unit circle. So accordingly, now we need we need a gain of 0. We need a gain of 1 at 0.4 hertz and a gain of 0 below 0.4 hertz. So the filter should look something like this. So that this is the baseline component, this is the PPG signal, and this is the power line signal. So we are going to design the filter as shown here. What we are going to do is we are going to place the 0 on the unit circle and a pole at omega equals to pi, or f is equals to fs by 2. The magnitude of the r determines the bandwidth of the filter. This r can vary from 0 to 1. Generally we keep it uh, close to the 0 or close to 1. So accordingly, what we can write is we can write the general transfer function h of omega as some gain into the z minus the zeros on the z minus the poles. Now, since we are keeping the pole at omega equals to pi, this minus sign becomes plus, so it is z plus r e raised to power j pi. So the e raised to power j pi component just becomes minus 1, so this is z minus minus r, that is z plus r, and the location of the pole is location of the 0 is z minus 1, that is at 1. If we go on solving this equation and find the value of r according to the given formula 1 minus 2 fc by fs into pi, we found out that the value of r is equals to 0.9685. According to this value, and keeping one more condition, that the gain of the filter should be equals to 1 when omega equals to pi, we can find out the corresponding value of g. These are the coefficients of the filter. These are also known as the filter coefficients. We can therefore derive a difference equation from the obtained transfer function, and this, once we know the difference equation, we can make the z transform, and like from the z transform we can find the magnitude and phase relations also. So once we found out the filter coefficients, they have the following values, and the difference equation is of the forms of the y out of I is equals to g is the filter coefficient, g into y out of I minus 1 plus k into xi minus xi minus 1. So x here is the input signal and y out is the output signal. We generally say that the values of y out for negative indices, the loops negative indices, and y out of 0 is 0. So we'll use this loop to find out the values of y out, and we declared these coefficients k and g already up above. So x is the input signal, and in just for comparison, what we are going to do is we are also going to plot the signal which is without the baseline, so as to see if our digital filter so as to see if our filter actually works or not. So this y without is the signal without the baseline component. So we have to compare the y out and y without the baseline and y output of our filter. They two should be matching. So we'll just upload the code and see the results on serial plotter. So here we can see that see, this is the input signal. The red one is the y without, and the green one is the y output of our digital signal. We can see that the input signal has a baseline component because we can see these mild variations in the shape of the input signal, and these variations are pretty much linear in case of the output signals. And we can see that the red and the green signal are pretty matching, so we can say that the filter design is actually working and we successfully removed the baseline component. Now that we know that we have designed a filter correctly, we need to visualize these baseline components. So one good way to visualize these baseline components is we can generate sine waveforms with the frequency of 0.1 hertz, 0.2 hertz, and 0.3 hertz with the respective magnitudes of 0.1, 0.2, and 0.15 using MATLAB. And then we can add these baseline waveforms to the original without the PPG signal without baseline, and see if we can obtain a very similar waveform to the one with the baseline. So I have generated these sine waves and added them together of respective frequencies and magnitudes, and we have got a resultant array called B1, which is 800 samples, and these are the values. So what we are going to do is, this is our x is the input for our this code. We are going to normalize this. We are going to normalize this input, and output of our filter will be stored into y out array. The same filter coefficients we are going to use again. So in order to normalize, we are going to divide it by the maximum value of the array. So here we are finding out the maximum value of the array. We divide each element by the maximum value to get the normalized array. Now in this normalized array, we are going to add the baseline component, that is b1 of I, on over the 800 samples, and then run this y normalized as an input to our digital filter to find out the y output. So let us see. Let's upload this code. Here we can see in the serial plotter, the green one is the baseline, and here are the y here are the values of y out and y normalized. So this is the y normalized is the uh, red one, and the y output is the blue one. We can see that this variation in the values as per the baseline shows that the baseline we generated creates these small variations, and it can be easily visualized this way. For the last part of this experiment, we have to remove the 30 hertz power line component. So we just have to change the input to the given filter to the one which is provided, the signal with baseline and the power line signal. And here we don't need any we don't need to compare it with the any other signal. So I just commented out this code, and we are just going to run this input through our filter, and let us see how it performs. So I've already uploaded the code. We'll see on the serial polar plotter. So here we can see the blue one. Blue one is the blue one is the input, and the red one is the output to the output from the digital filter. So this was experiment number 6.